Hey guys, in this video I'll be dealing with the second part of a two-part problem. So in particular, I'm going to be dealing with how much does the spring compress? What is the maximum compression due to this block hitting it when it's released from rest up here? Okay, well, in order to solve this particular problem using energy methods, we need to recite the work energy formula, which is the change in kinetic energy plus your change in potential energy plus your change in elastic energy is going to be equal to your work done by non-conservative forces. Simple enough. But what I'm going to be introducing you to is the concept of a whole new state. Remember, I defined state 1 as being where it's released from rest up here. I also defined state 2 as where it just hits the spring just here, that's state 2. And I'm defining state 3 just here, state 3 to be where the spring is at maximum compression, state 3 just here. So when I'm going to be applying this formula, I'll be applying it between states 1 and 3. Although I could have chosen state 2 and 3 if I liked, but I think you'll find it'll be easier for 2 and 3. So when we expand this formula out, we'll be dealing with a half m times by v3 squared minus v1 squared plus mg h3 minus h1 plus half k x3 squared minus x1 squared, and that's going to be equal to your work done by non-conservative forces. Okay, now we need to draw a free body diagram so we can get an understanding of all of these variables. Let's start our free body diagram just here. We know this right here is our tube just here. We know our block at some point during mid-flight looks like this, and of course we've got our forces acting on it. We've got mg downwards, we've got our normal force, of course normal to the path, and we've got our friction force, arguably the most important, which is going up just here of mu k n just here, and this is your normal force. Now I've already solved this particular type of thing in the previous problem, but basically n was shown to be equal to mg cosine theta. I won't be proving in this particular video, I've already done in the first part, right? Now remember, your work done by non-conservative forces is equal to the force you're applying to your block times by the distance moved in the direction of your force, which is equal to, in this case, mu k times by n, which is mg cosine theta, times by the distance moved in the direction of your force, which is negative 0.5, is that it? Not quite, minus delta, where delta is the compression of your spring. Basically, your block moves from state 1 to state 3, a distance 0.5, plus that little extra bit of compression of your spring, delta. That's a really important point to remember, right? That can't be avoided. Now that we've got our work done by non-conservative forces sorted, let's see if we can evaluate the other terms. Let's start off with evaluating H1 and H2. We know that if this right here, let me draw it right here, if this right here is state 1 just here, and this is what will define our x and y axis just here, x and y just here, then H1 must be equal to 0. Let me keep the colors from going crazy. This is H1, which is going to be equal to 0, and H3 is going to be this distance from here to our state 3, which is going to be here, just there. Right? Fortunately, we can use trigonometry to help us solve this, and we can say H3 is going to be equal to minus 0.5 plus delta times by sine theta. I hope I'm fitting all that in. I think I'm running out of space. So we can rewrite everything now. We know this will turn into a half times by m times by v3 squared minus v1 squared, I'll get to that point later, plus mg times by h3, which is minus 0.5 minus delta sine theta. Notice h1 is 0. I think that's right. Yep, good. And now let's deal with this red term. This is going to be a half times by k times by x3. Now x3 is where your block is in its third state, which is when the block is at maximum, when the spring is at maximum compression, and I've defined that to be equal to delta. So it's going to be delta squared, right? Now let's sub in our work done by non-conservative forces. I don't have enough space, I'll do that in the next step. Let's leave it as WNC. And now let's zoom out and plug everything together. We're almost done, actually. So let's plug everything together, and this is what we're left with. And this is what we're left with. Notice that V3 is going to be equal to 0. It's going to be equal to 0 because the block is at the point where the spring is at maximum compression, which is where the block stops for an instant. So V3 is 0, V1 is 0 because the block is released from rest. So this term all boils down to mg times by minus 0.5 minus your compression of your spring sine theta plus a half k delta squared, and that's going to be equal to mu k mg cosine theta times by this beast right here, which is minus 0.5 minus delta. Now remember, the whole point of invoking this equation is so that we can solve for the maximum compression of our spring. Remember, delta equals maximum compression of spring. Should have written that down earlier, but I hope you understand. So we're going to solve for this, and we're going to be dealing with a quadratic soon, as you may have guessed already. Let's bring all the deltas over to the left-hand side. That's going to be a half times by k delta squared. Now there's a delta over here. Let's account for that. So we'll be leaving that with minus mg sine theta times by delta. Notice there's a delta over here, so we can bring that over to the left-hand side as well. So we'll be dealing with plus mu k mg cosine theta, right? And that's going to be equal to what's left on this side, which is mu k mg cosine theta times by 0.5, or minus 0.5, I should say, minus 0.5, and what's left over here, which is going to be plus 0.5 times by mg sine theta. I'm running out of space again. There we go. And once you evaluate all these terms out, this is what you get. Alright, this is what you get. You're left with 800 delta squared minus 13.067, that's 067 delta, and that's going to be equal to 6.533, right? Notice that this will involve a quadratic. So we could, if we wanted to, complete the square, but I think it'll be easier to use the quadratic formula. And if you use the quadratic formula, let's actually make this in the form of a squared plus b 0.67 and then minus 6.533 is equal to 0. Right? And once you use the quadratic formula, you'll be left with two results. You'll be left with delta is going to be equal to either 0.0989 meters, or delta is going to be equal to minus 0.0826 meters. And just in case you've forgotten, you probably haven't, but just in case you've forgotten, the quadratic formula states minus b plus or minus the square root of b squared minus 4ac all over 2a. This is a, this is b, this is c. Okay? Now, here it becomes a matter of common sense. This value is clearly the correct one because it's positive, right? You can't have a negative compression of your spring. Well, I guess you could, but that would be expanding it out, not compressing it. And clearly in this particular case, the spring is being compressed. So this is definitely the value which is true. This is your maximum compression of your spring.